Today in this video, what I'm going to talk about is how to solve a complex ion equilibrium problem, right? And understanding what the molar solubility is for a salt when you add or have in solution something that can also bind to it and that actually improves the solubility in most of the cases. So in this problem right here, right, the question is basically just to calculate the molar solubility of silver chloride in a 1.0 molar solution of ammonia. Right, aqueous solution. So what we're given are two values. So we're given the K of formation, right? So the formation equilibrium constant for the silver amine complex, and so that's going to be 1.7 times 10 to the 7. Then we're also given the solubility equilibrium constant for silver chloride, which is 1.6 times 10 to the 10. So first things first, for any of these types of problems, I would always recommend to write out what all of the individual reaction steps actually are that you're looking at, right? So the first thing we can look at is the formation of the silver amine complex, right? So the way that that'll work is that you'll have silver plus ion in solution, right? So that's going to be aqueous plus ammonia in solution, and that's going to be in equilibrium to form the silver amine complex, right? And so you're going to have two ammonia molecules binding to the silver in this case, right? And so you just have to make sure that you have two in front of the ammonia within the overall expression. Apologies for if you hear my wife in the background. She's upstairs with my kid. Right, and so this is right here is what you have for the formation. So if we just go through, right, so Kf in this case right here, we just write out our equilibrium expression the way we typically do it. And so that would just simply be then up top, we have the concentration of the silver amine complex. And then at the bottom, we would have the concentration of silver plus, and then the concentration of the ammonia, right? And then the ammonia, because it has the coefficient of 2 within the equation, right, it's going to be to the power of 2 in that case. And so that's equal to 1.7 times 10 to the 7. Now next, the other reaction that we need to think about and determine the equilibrium for is then just simply the dissolution of the silver chloride into water in this case, right? So what we have is solid AgCl, right? And that's going to then be in equilibrium to form Ag plus aqueous plus Cl minus in this case, right? And so the equilibrium expression in this case, right, is going to be the solubility product expression, so KSP. That's just simply going to be then equal to the concentration of Ag plus times the concentration of chloride ion. And so that is equal to 1.6 times 10 to the negative 10. Right, and so we have those two values right there. Now we can write out, what the full reaction is, right? So if we have those two reactions together and we add them up, what we get is, right, looking at it, the silvers are going to cancel, and so you're going to have as your reactants silver chloride solid plus the aqueous ammonia solution is going to form the silver amine complex plus chloride in solution in this case. So we can just write that out, right? So that's AgCl solid plus 2 ammonia molecules aqueous to form our silver amine complex plus Cl minus. Everything's balanced, everything matches up in this case. And so for just how it is for any kind of equilibrium problem, when you're adding equations together, right, different reactions together to determine what the equilibrium constant is going to be for essentially the amalgamation, right, the combination of all of them, all you have to do is just simply multiply the equilibrium constants by each other to get then what the equilibrium constant is going to be for that, combined reaction in this case. So for this reaction right here, right, K is going to be equal to Kf times KSP, right? And the way that we can kind of prove ourselves, right, that that's all going to work out is if we just simply take the equilibrium expressions right here and we can see things canceling out for themselves. So we have Ag NH3 plus up here, right? We have the silver amine complex over Ag plus times concentration of the ammonia squared. And now this is going to be then multiplied by the KSP in this case, right? So that's Ag plus times Cl minus, right? And so then the concentrations of Ag plus cancel out. So what we get, right, is that K is equal to the concentration of the silveramine complex times the concentration of the chloride ion over the concentration of the ammonia squared, right? And so that's our equilibrium expression. So that matches exactly what we have over here from the left side. So now the way that you approach it, so we can get the K, right? And so we have the KF times KSP. So I'm just going to go in real quick actually and just simply calculate that out. And so what I got was that by multiplying the KF times the KSP, what you get is an equilibrium constant of 2.72 times 10 to the negative 3. In this case, right? So that's our K value for this reaction, right? The silver chloride being dissolved and binding to the amine and so forth. So now the approach is we do an ice table, right? And so in the ice table, because we're talking about equilibrium, right? The solids just don't contribute, so we can disregard that. We have, starting off 1 molar of the ammonia in solution, right? So we have 1 molar in this case. We don't have any of the new silver complex, right? The silveramine complex that's forming, that hasn't happened yet. We also don't have any chloride, right? Because the silver chloride hasn't dissolved yet, right? So both of those are going to be 0 in this case. And so then now, right, the change, we're going to lose 2x of the ammonia in the solution. We're going to gain x of the silver amine complex, and we're going to gain x of the chloride. And so at the end, what we should have is 1.0 molar minus 2x of the ammonia, and then x of the silveramine complex, and x of the chloride ion in that case. So all we have to do, right, we can just simply take that, plug that into our K expression over here, right? So K is then going to just be x times x over 1.0 molar minus 2x squared, right? Don't forget that squared part right there. And so that's going to then be equal to the 2.72 times 10 to the negative 3. So if we go through, right, and then just solve for x, right, just do our algebra in this case, what we get is a value of 4.72 times 10 to the negative 2 moles per liter. And that is the molar solubility of silver chloride in a 1.0 molar solution of ammonia in water.